Density is defined as mass per unit volume. In other words, how much material is inside a given space. Density can be expressed in many ways. The first way you've already seen. This is grams per cubic meter. Or in standard international units, kilograms per cubic meter. If you remember from the lesson on the atmosphere, we talked about the standard atmosphere or ISA. At sea level, ISA stated that the density was 1225 grams per cubic meter. So we have a mass, which is 1225 grams in a volume, which is 1 cubic meter. However, there are other ways in which density can be expressed. If we know the standard sea level density in ISA, then we can use this as a benchmark to compare densities from other areas. So we take the density of 1225 grams per cubic meter as 100%. If another area has a density of only 1000 grams per cubic meter, then this density is approximately 82% of the ISA surface density. We call this expression of density relative density. We are comparing the density in one area relative to the density in ISA at sea level. Another way density can be expressed is by using the term density altitude. Training pilots seldom understand this term, but it is essential, especially when using it to discuss aircraft performance. However, before we analyze this term, let's first look at the two main variable factors that can influence density. These are temperature and pressure. Looking at the diagram, we can see the density formula. Notice that in the formula, we replace density with the Greek symbol rho. We'll now look at how the variables of temperature and pressure affect the mass or volume and therefore the density. Let's first look at how pressure can change density. If we look at the diagram, we can see a mass within a volume. As we increase the pressure surrounding the parcel of air, you can see that it gets compressed. This causes the density to increase. We are keeping the mass the same, but reducing the volume. Conversely, if we reduce the surrounding pressure, the parcel will expand and the density will reduce. Again, the mass is the same, but this time the volume has been increased. Physical experiments confirm that density is proportional to pressure. The other main variable we mentioned that controls density is temperature. Looking at the diagram, we can see that as we heat a parcel of air, the particles get excited and cause the parcel to expand. This reduces the density. The mass is staying the same, but the volume of air is increasing. Conversely, if we cool the parcel down, it will shrink, and the density will increase. Again, the mass is remaining the same, but we are reducing the volume. We can therefore say that density is inversely proportional to temperature. Having seen the effect of varying temperature and pressure on density, let's now consider the effect of altitude on density. Here we have a conundrum. As altitude increases, temperature falls, therefore density should increase. But as altitude increases, pressure also falls. This causes the density to decrease. So what does happen to density with altitude? The overriding effect is the change of pressure. The reduction of pressure reduces the density more than the reducing temperature causes density to increase. Since pressure is the dominant effect, it follows that because pressure decreases at a decreasing rate with altitude, so will density. Looking at the diagram of ISA, we can see that relative density decreases with altitude at a decreasing rate. Having seen the effect of density with altitude, let's now consider how density changes with latitude. Looking at just the surface conditions, we can compare the poles to the equator. From the diagram, we can see that at the poles, the temperature is generally colder, and the pressure generally higher than at the equator. The combined effect is that at the surface, the density at the poles is greater than at the equator. However, at altitude, the effect is different. If we remember from the pressure lesson, we stated that cold air increases the pressure lapse rate with altitude. In other words, pressure falls more rapidly with height in cold air than in warm air. Because density is strongly linked with pressure, it therefore follows that in cold air, density would decrease more rapidly with altitude than in warm air. As a result of this, over the poles where we have cold air, the density at a high flight level would be much lower than at the same flight level over the equator. At high altitudes, we can say that density decreases with latitude. There is one more variable that can alter the density of air. This variable is water vapor. The effect is complicated and beyond the scope of the expected level of knowledge needed. It's sufficient just to know that the density of water vapor is less than dry air, such that if a parcel of air was to contain water vapor, the density would be less than that of a parcel of dry air. If you remember from earlier in the lesson, we mentioned density altitude. Having seen the effect of all of the variables on density, the expression of density altitude can now be better explained. Density altitude is simply defined as being the altitude in EASA that the prevailing density would occur. This is best explained by using an example. Let's say we are at sea level, and the atmosphere happens to be exactly the same as standard. The density at sea level in the real atmosphere will therefore correspond exactly to that found at 0 feet in EASA. However, now let's increase the temperature of our location at sea level. We now know that the density will be less. This new lower density at our location corresponds to a density found at a higher altitude in EASA. In our example, we can see that the density at sea level in the real atmosphere equates to a density found at 10,000 feet in EASA. We therefore say that the density altitude of our location is 10,000 feet. The knowledge of density altitude is important in assessing the effect of the changing density on aircraft performance. We'll cover this later. But for now, let's see how we can calculate our density altitude. There are two simple ways of calculating the density altitude. One method is by using a flight navigational computer, and the other is by using a simple numerical formula. This formula states that for every 1 degree Celsius away from EASA, depending on whether the deviation from EASA is positive or negative, you add or subtract 118.8 feet to your pressure altitude to find your density altitude. Now let's look at an example. Let's say the pressure altitude is 2000 feet and the temperature is 25 degrees Celsius. This means the atmosphere is 13.96 degrees warmer than EASA. Therefore, the EASA deviation is plus 13.96 degrees Celsius. We can now see that the density altitude is 3658 feet. Most density changes are accounted for in performance graphs by the use of altitude and temperature nets. The example shown is the landing distance graph for a small single-engine aircraft. We'll now look at the importance of density changes on aircraft operations.